Hello, my name is Brooke Weaver, and this is my Lab 3 on the magnetic field of a bar magnet. In this lab, it was important to understand that the magnitude of the magnetic field proportionally changes with its separation distance from a particular source. We aim to study the magnetic field produced by a bar magnet by using our smartphones to determine the numerical factor that the separation distance impacts the magnetic field. The system will be isolated to a magnetic field caused purely by the bar magnet, and the results will be compared to the computational model. In this lab, the distance dependence factor was calculated to be -3. The magnetic momentum mu is calculated to be 2.965. The experimental net magnetic field at 45 degrees was determined to be 4.821 e to the -5th. The computation model yielded at 2.031 e to the -5th. One of the fundamental principles is that the Earth also exerts a magnetic field. To isolate and study the bar magnet's magnetic field, it must be placed perpendicular to the Earth's field. Further, the Biot-Savart law is crucial to this experiment as it relates to the magnetic field to the separation distance of a magnetic moment. The distance dependence equation for the magnetic field is important to calculate the distance dependence factor and the magnetic moment. In part 1 of the experiment, we first had to compensate for the magnetic north and locate the magnetometer chip in our phone. Then the bar magnet was placed at different distances to determine a x component value for the magnetic field, and the distance was recorded. After performing 3 trials for each value, the spreadsheet produced a graph which could be used to determine the necessary calculations. The spreadsheet of my data is to the left, in which all the yellow boxes include my typed-in data. The graph to the right is important as I will use the linear equation produced to calculate m and mu. Using the equation from the graph, the distance dependence factor and is seen to be equal to the slope, which exists approximately to -3. This means that the magnetic field is inversely proportional to the cubic distance. Then the magnetic moment can be calculated by setting the distance dependent equation to modified Biot-Savart equation. The value of k can be calculated by raising e to the value of natural log of k from the graph. The magnetic moment can be solved for, which was found to be 2.965 amps times meter squared. In part 2, the bar magnet was placed at a distance where B net equaled 100 microteslas. The y component was recorded, and the phone was moved vertically upward to the same perpendicular distance. At this 45-degree angle, the x, y, and z components of the magnetic field were recorded, and the y component was adjusted to account for Earth. This is my data from part 2. As can be seen, the average experimental vector for the magnetic field produced at 45-degree angle at an average distance of 0.285 meters is 3.167 10 times 10 to the -6, 2.186 10 to the -5th, and -4.277 10 to the -5th teslas. The average magnitude thus is 4.821 times 10 to the -5th teslas. A computation model was constructed to calculate the magnetic field at a 45-degree angle. These are some important sections of the code. First, a function called dipole P was created to calculate the magnetic field due to a dipole of a particular locations. 2 on-axis locations and 4 perpendicular locations were created, and arrows represented by the magnetic field at these locations. As example, for on-axis location number 1 and for perpendicular location number 1, it can be clearly seen how these 2 different arrows were created. This code was repeated for each arrow created. To calculate the magnetic field at 45 degrees, I import the deeper value and observation location, then use the D and dipole B function to calculate the value. The visual of the 4 sign arrows represent the electric field at 4 perpendicular distances. The 2 orange arrows represent the electric field at 2 on-axes. In the code output, the magnetic field at perpendicular locations are correctly half of the magnitude of the on-axis magnetic fields, and the magnetic field at 45 degrees was calculated. The computational experimental model can be compared, and due to their magnitude differences, the computational model had nearly 2 times in the x component, and additionally the computational model had no z component in comparison to the experimental value. For the concluding questions, for the what-if questions, the answer would be that the Earth's magnetic field would have impacted the measured magnetic field, making the results less accurate. And for the imagine if you had 2 identical magnets, the magnitude of the magnetic field would be stronger and the direction would not change because the magnets are end to end and are working with each other. Thank you for watching.